Hi, and welcome to the first day of our training. Um, we might start with something very basic. Why is R worth learning? I mean, if you're a data scientist, you probably already speak some Python, or if you're a computer programmer, Java or C++ or whatever you want to go with. So why do we need a language for biostatistics? Well, R is not really, maybe didn't start as a language that's brilliant for biostatistics. But R is extensible, which means that people can create new libraries for doing new things in R. And when they make those libraries available to us, we can do those advanced and cool things. So let's talk about advantages and disadvantages. I want to write a paper, right? I'm a grad student. I'm trying to get my first paper out the door, and I'm going to need some figures that show the data I got back from my study. I think most of us have knocked out a bar chart or two in Excel over our times. Would you feel comfortable putting a bar chart from Excel in a science paper? Got a head shake? No, no.
Yes,
Okay. Yes, yes for you. Okay.
if you modify it with Illustrator, so like
He'll tweak it after the fact. Okay. So for somebody who is shaking your head no, what is it that makes you feel an Excel figure is not in your interest to improve? It doesn't look professional. Okay. So we think that uh, the images from Excel are recognizably from Excel. Okay. And if you put a figure in your paper that anybody could make, maybe your work doesn't look as distinctive. I'm kind of extrapolating from what you're saying here. So I, in general, I think all of us end up using Excel some amount in our research. It's very frequently the case that bioinformatics tools are kicking out TSV files, and we need to just browse them. So we knock them open in Excel, and we're off to the races. Maybe you compute some t-tests in there, right? But would you, for example, try to fit a multi-factor linear model in Excel? Can you?
yes,
You can. You can.
yes,
Yes, you can do a straightforward linear regression, certainly. I don't know how to do a multi-factor one, but it seems likely that at least with given plugins, you could.
Is it good enough?
Is it good enough? It is definitely the case that if you want a statistical model that is very carefully vetted, that's using best practices for minimizing error and so on, I think you're a lot more likely to get that result from R than you are from Excel. Do we have users of GraphPad Prism here? Quite a few. Yeah, GraphPad Prism is quite capable. And yet GraphPad Prism is also very intent on user experience, perhaps, and less on the tightest of rigor, perhaps. I don't want to besmirch their product, but I will say that I see GraphPad Prism as a real step up in sophistication and in publication quality graphics and stuff like that. I do feel its interface is kind of limiting in the kinds of things I would like to do. So a long, long time ago, there was a commercial product called S and S Plus, and this statistics environment became very popular, but it was also fairly expensive. And people in the open source community thought, wouldn't it be great if we had an S that was open source and that we could modify however we wanted? So instead of calling it S, they called it R. And that's what we're going to be learning in here. I really like teaching R in a class because it's free. Anybody can download it. It works multi-platform. So if you've got an Apple or you've got a Windows machine, I suppose if you have a Linux machine, that could happen. All of us can run R equally well. If you have a Chromebook, I don't know. Maybe it'll work there. The same code that I run on my Windows PC you can be running on your Apple PC, your Apple computer, and it'll work just fine. So I think it's a really valuable training opportunity. And in some cases, when I've arrived at a site and discovered that the Wi-Fi for campus wasn't working, we could all work together in R, and it was usable, where all those web demos I had planned for the session wouldn't. So I'm glad to get this chance to work with you in R. R has been a friend of mine for a long time. I met R in grad school. And I'm going to mention an experience that, let us say, could only happen in America, but I suspect no, it happens everywhere. I was in grad school. I had produced a bunch of statistics about fragment ions I had seen for confidently identified peptides. And I had generated all these charts and graphs, and they were great. They were really great. And my PI said, I want to see what this looks like with a larger data collection. Can you just regenerate that sheet with this new set of data? And I was really frustrated by that, because all of the equations and figures that I'd put together in Excel had to be recreated, because the analysis, those figures, those statistics, was not separable from the values upon which they were based. I couldn't just throw in a new table and point all those formulas and graphics to look at the new table. So R is brilliant for stuff like that. It does a very good job of separating input data from the operations you're going to use on them. And if you run this on the first 10 samples, decide to shoot another 50 and include those in the analysis, it will scale very well with you. But R is programming. It is programming. It counts as programming. And not everyone's comfortable there. So I want to start at a pretty basic level today. I hope we get through this whole file. I'm looking at RA, Essentials of R Programming and File Access. It was one of those files you should have grabbed off of the thumb drive. So if you don't have it, here's your chance to grab it. Everyone has it? Good. And we're going to just start with how R works. Now, I'm looking at this in Emacs at the moment. Please don't be distracted by that. It means I'm old. But you can look at this in Notepad or Notepad++, any text editor you like, really, and it'll work just fine. This is the script that we're going to go through. And this script is going to help us learn a few basics of programming. Who in this room has had at least one class in programming in their lives? Oh, good. Okay. So whether it was Python or Java or whatever, I don't really care too much, because they're all general purpose programming languages and they all look pretty similar. So let's try to work our way through this. I've started R in the background here. You may have set up RStudio on your computer instead. That's fine. RStudio will also work quite well. I'm going to run R here because it means that I can show the text larger. And I want to check that everybody at the very back of the room can still read the text on screen. All right, now my eyes are 50 years old. I need to sit a little closer. But I'm glad that works for you. If you have problems with vision, let me know and we'll work it out. But if that fails, we hope to have a recording of this that we can make available to you guys. All right, so here's R. It's telling us I have started. Right. I'm using R version 4.6 here. Does it matter that you have exactly 4.6? No, not in the least. Probably if you drop back to version 3, something would probably break, but it's been a while. Most of this R code is quite stable over time, so you shouldn't expect things to break just because you go from 4.6.0 to 4.6.1. Okay. The way that we enter commands in R is to type them. In this case, I'm going to grab out this first block of text down to the letter C by itself, and I'm going to paste that into the browser. Paste that into R, rather. Okay, we have what we've done here is something that you probably had to write in middle school, probably before that. When you took pre-algebra, you had to deal with variables, right? So in this case, we have a variable called A, and we have set its value to 2. we have a variable b, and we have set its value to 5. We create a new variable c, but here we don't explicitly tell it what value goes in there. We've given it a formula that it must compute to create the value in c. It's going to add together a and b. And out pops the variable c. If I just type c by itself, it reports its value is 7. 2 plus 5. Okay, this is a really simplistic understanding of variables. I would say that if you're used to something arcane like Pascal, but probably more like C or something like that, you were dealing with a typed language where you had to specify that variables were of type integer, and then you could set their type here. We don't have to do that. R says, if you want to tell me A equals 2, I'm down with that. If you were to tell it that A is Bill, and now say C equals A plus B, now we've got a problem. Okay, so this is not a strongly typed language. It'll allow you to set that variable to whatever you want. But if you're going to add things, they need to be of the same type. Okay, great. So that's a start. Now, are variables required to be atomic to represent one and only one value? No. No, and this is really where things go right around the bend with R. You can have quite a variety of variable types, but we'll talk about that as we go on. Let's talk about Booleans. All right, I'm going to copy this next segment out. This might seem a little different than the algebra of the past. So in this case, I have set A to be equal to true. It's Boolean logic now. And B has been set to false. In this case, rather than setting C equal to something, I'm just computing the value directly, right? So here I'm saying A ampersand ampersand B. In this case, ampersand ampersand means and. Okay, so if A is true and B is true, then what returns from it is true. But if either of them is false, it returns false. It's just the Boolean and logic that we've all come to know and love. And down here, we see that if we instead use pipe symbols, A pipe pipe B, it understands that as an OR function. So if A is true or B is true, then the result is true. And in that case, we get the value true. So sometimes our operators are going to be one character, and sometimes they're going to be two. And it's kind of worth keeping that in mind. Okay. So next, I'm going to just do away with the variable labels for a moment, but you remember that we could always replace these with A or B if we wanted. Now I'm using some expressions here, again, using operators that are multiple characters. So greater than equals means is greater than or equal to. So is 5 greater than or equal to 7? No, that's a false. 4 equals 4. Now that looks like kind of a weird operator, doesn't it? We've been using equals a lot so far. Remember we said b equals 5, b equals 2, whatever it was. But now, instead of using equals, we're using equals equals. So sometimes when you repeat these symbols, they have different meanings. In this case, we're asking a question. It's a conditional operator. We are asking, is 4 equal to 4? That's true. In the next case, we negate that. When we see an exclamation mark, a bang in there, that is to imply the opposite of. So 4 is not equal to 3, that's true. Does this make sense? So if I were to say, is 4 not equal to 4, that's false, because 4 is equal to 4. If I say 4 is not equal to 3, that's true because they're not the same. Okay, so these operators all exist. Some programmers are going to slip them in there and just assume you caught them. but it's probably worth taking your time at the start to just watch those operators as the code scrolls by and try to remember how they're working. And I'll try not to just blast a whole bunch of functions on screen and assume you're following me. Our classes, taught by experts at least, tend to be aggressive and not friendly. I'm going to try to make the first rung of the ladder here. So if you're going to take an R course, you will at least be prepared for the shell shock that's coming. And if you feel it's not useful and you want to see the advanced stuff, we'll be done fast. But I'll try to walk through slowly at first. But what is our critical drop dead moment for this training? 12:30. That's lunchtime. Lunch is holy. Okay, so on we go. Right. So I have the little note in here. You can see that when you're writing a script, you can tell the software to ignore it. So when you see the hash symbol, what do
The comment?
yeah, the comment symbol. Yeah. What do people call that a hashtag symbol now? I don't. Yeah. Okay. Good.
How would you call
See, it's been called a lot of things over my career. Some people call it the tic-tac-toe.
it? Oh my.
Yeah. The hash symbol, the number symbol, like we're number one. Yeah. So it gets called a lot of things. Yeah. Okay. So if you see me call it hashtag, then I'm just being silly. It's okay. Right. Okay. I promised you that we would look at things that are not atomic, not like five, like A equals 5 or something. So for this, we're going to talk about vectors, and vectors are where R starts getting muscular, right? So let's walk through this. So I've written my little note here. R has superpowers when many numbers need the same operation applied to them. Vectors let us do many operations at once. So let's just run this first bit of code. All right. Now I've broken in something new here, and I want to be careful about doing that. So you see this C here? This C is not variable C because it's followed by a parenthesis. So this is a function. This is the compose function. So anything inside these parentheses are inputs to a function called C that creates, in this case, a vector out of those numbers. So A's value is 284338. Remember, we can just type the letter A and hit enter, and it'll show us that. Okay, so these variables are no longer equal to a single value. They're equal to a series of values. So these are vectors. Here, B has been set equal to the same number of items. A is 5 items long, B is 5 items long. And now, sums is adding the two of those together. Now, I want to contrast this with a couple other possibilities here. So let me do sum A, sum B, sum sums. Okay. Now, I've just made this worse in some ways because sums here is a variable. It's a variable that receives what happens when you use the plus operator to add these items together. So the 2 gets added to the 21, here's 23. 8 gets added to the 7, that produces the 15. 43 gets added to the 9, that's a 52. Everyone sees how that's working? Okay, so adding together two vectors adds together corresponding items of those vectors. But things got crazy down here, because down here, I'm no longer talking about the sums variable. I'm now running a function called sum, and I'm running it on A, all of A. And in this case, if you run the sum function on a vector of values, it adds them all together, and that's the output, 64. Now, again, I could capture that by saying C equals the sum of A, and that would be fine too. Here's the sum of B. and here's the sum of sums. Oh, now we've gotten a little arcane and weird here. So sums was the vector 23, 15, 52, 37, 12 that we got when we added together A and B. And now I'm running the sum function on the sums vector. And it's adding all those values together, and that's the output. Because that's what the sum function does. But hopefully this has given you a little bit of a marker in your mind that, a function and a variable are rather different things. Okay. Yes, please.
Because I don't know the word vector. So a vector is this string of things that are like in a parentheses,
Yeah.
maybe the number, or it could be whatever.
Yes.
Okay.
Yes, you could make a vector of names of students in a class, for example. So let's create a vector called names equals, all right, so I've got Bongani, I've got Ndiko, I've got Ashwell, I've got Lysics. These are all friends of mine from South Africa. Okay. That is a vector, yes. Yeah. Yeah. I'm trying to think, can I give you a concrete definition of a vector? But I think for now, I'll call it a 1D collection of items of the same type.
So in R, the vector is not the vector in mathematics.
It's sort of, and sort of not.
Yeah.
Yeah.
In mathematics is just numbers.
Right. So let's try mixing it up. Here's multi. Multi equals C Bongani 73. That's my lucky number, everyone. Okay, and now James and true. Did the software barf? No. It was happy with that. Okay, but something sneaky has happened. We provided it strings, the names Bongani and James, a numeric value, and a Boolean. What resulted, though, in the vector that resulted?
Yeah, transform the.
See the double quotes? Yeah, so 73 is no longer a number. This is the string 73. True is no longer a Boolean value. Now it's true. So if in doubt, the software is going to coerce things into the same format to shove them into a vector like this. Okay, that was a good divergence. Thank you. That's not in the script, but it's worth talking about. Okay. Now, let us talk about what happens when the vectors are different sizes and you do nonsense like this. Okay. Great. So, A is a vector 1, 2, 3, 4, 5, 6. B is the vector 0, 1. They're different sizes. I create a new variable called alternating where I add them together. And this is what results. What on earth happened? Can you see it? Are any of the numbers unchanged?
The odd ones.
The odd and even, exactly. Yeah. So 0 got added to 1. 1 got added to 2. 3 had to be added to 0 again, right? So it's going to restart. Now, what happens if this is 1 through 7 and that's 0 and 1? I'm going to just run the example because why not? All right. This time, I'm going to make the first one. See, now we have an error. So it was fine for if we add these two vectors together, because this one is 6 items long and this one is 2. So then it assumes you just want to repeat this one 3 times. But in this case, I have one vector that's 7 long and the other was 2 long, 2 items long. It couldn't add those together without at least a warning. Okay, so the software has some odd behaviors when you tell it to add together vectors of different lengths. Okay, doing okay so far? All right. I realize that a lot of this looks like some funky math, but it's useful, I think, in understanding the limitations of the language and its expectations, frankly, of us. Okay, I'm going to come back up here and rerun this code. Okay, there's my sums. Great. So we can pull out individual elements. Okay, so the square bracket operator is pretty important. Very frequently, you have a whole bunch of numbers in a variable, and you want to grab out a subset of them. So sums was 23, 15, 52, 37, 12. We tell it we want the second element drawn from sums, and the square array operator pulled that out for us. That the number 15 is what results from that. Okay? Great. So we're getting good results now. Often we don't care about everything in the table. We want to know just about that one row. So this is valuable stuff. Now, let's look at this more complex form of it. What happened here? Remember that the create function, compose function, I forget the name, sorry, is given two numbers here. It's given the number 2 and it's given the number 4. That vector is then passed into the subset operator. So sums was 23, 15, 52, 37, 12. We pulled out the second element and the fourth element, but not the third element. Okay? All right. Now we're going to use a series operator just to make this even a little stranger. If you want to describe all the numbers from A to B, you can use the colon operator here. So this is very slightly different than the last command in that we're giving it the square brackets operator, the series, the vector 2, 3, 4, because we told it 2 colon 4, which means the number series running from 2 to 4. The command just before that, the C2 comma 4, is only giving it 2 and 4, but not 3. Okay. I feel like I'm going, I know it might feel like this is the worst sort of drudgery, looking at all the different twisty ways that the software works, but it will help, I think, as we move further into actually using R for stuff. So I'm glad you're sticking with me. All right. Sometimes we would like to make fairly long blocks of numbers based on a series. So here, I provide the numbers 1 through 20 inclusive, because it's got the colon between them. And I'm going to multiply the number 2 by that. So this is another case, actually, where we have vectors of different lengths going into an operator. We have a vector 2 going in alongside the vector 1 to 20. So we're telling it, just keep reusing this 2 for all 20 of these elements. And out pops 2, 4, 6, 8, 10, etc., up to 40. And remember that we end at 40, not 20, because 20 was the last of the series, and it was multiplied by 2. I don't remember if I've included this earlier in the code, but I just wanted to say, you'll see a lot of code that uses a form like this instead. That's intended to be a little arrow pointing to evens, which is to say, even the variable named evens receives this value. It's, for most practical purposes, the same thing as the equal symbol. Don't worry too much about the fact that they look different. One is the other for most purposes. I think if you had an expert R instructor in here, he or she would cringe when I said that, because there are certain circumstances where they apparently differ, but I can't remember what they are. Okay, so for most purposes, whether you use the left pointing arrow or the equal symbol, it's going to be just fine. Great. All right. Here we're just providing a single operator series, numbers 14 to 20. There's no requirement that you start with number 1 in using this operator. Frankly, even if you don't know in advance which numbers you're going to use, let's say A is 40, A is 40 and B is 60. series can be from A to B. That works just fine as well. Okay? So anytime you see a number or an explicit value, you can provide a variable instead. That's okay. Right. Now let's go to a couple other odd functions. So let's talk about the repeat function. So let's think about which ones we've seen so far. We've seen C, the compose or create function. We've seen sums. Have we seen others so far? Can't recall off the top of my head, but what's that?
Function?
No, it was an operator. The colon is an operator. But I take your point. Yeah, it's sometimes difficult to draw the distinction between those. In this case, I'm using the repeat function. And this time I'm going to repeat NA that's not in quotes 10 times. So there's some trickery going on here. What is NA? Is that a string? How does it differ from a string? Let's show what this looks like. Okay. Does anyone remember the old Batman program? It used to be on TV many centuries ago. Batman. Okay, well, I always think of that when I see repeat NA 10 times, but it's okay. So this is what we get when we repeat na 10 times. But if we made it a string instead, the result is different. So what does NA represent here, since it's not a string, the way I had it written? It's this way. What's that? A vector. Well, if I just say what is the value of NA, it says its value is NA.
It's a variable.
It's a
Variable. Integer.
Not quite a variable. It's actually a special value, like true or false. NA means not applicable. Yeah, very, very frequently when we're looking at tables of a particular variable, we'll find that some of the values can't be computed or haven't been computed or aren't provided in the input table. And as a result, they are given a value of NA. And they come into play frequently where you don't want them to. So you're making a bar chart and the software complains because there are NAs reported for a variable. Where do you put that on a box plot, you know? So NA is a special value that we need to keep thinking about.
So if we don't put NA, it will be error.
I'm sorry?
If we didn't put NA, let's say XA, it will say error. We'll not consider it in the...
Yeah, XA doesn't exist yet. Yeah. Now, it's possible that I'm not coming to R freshly and resumed an old work session I was doing. And if I did that and had defined XA in the past, I would see a different result for that than you would if you were just starting R for the first time. So remembering which workspace you're in is actually kind of a big deal. If you're starting with a neat one, none of the variables will be defined, but NA will still exist because NA is a basic value that R knows about. There are a few other special ones, though. How about any mathematicians in the room? Will this bother you if I run this code? Let's do it. Oh, look at that. The software did not bark. It didn't say division by zero error. Instead, it gave me inf. Inf stands for infinity. And what kind of infinity does it represent? Always wanted to ask that. Are all infinities the same? This is positive infinity. And there are certain circumstances that would give you negative infinity as well. If you were to take the log of a negative number, no, one second, let me see. I should remember this stuff, sorry. Sorry. Now that's definitely not a number right there. So not applicable and not a number are not quite the same thing. So in this case, taking the log of -5, because that's undefined on the function, gives not a number. Okay. Cool. So there are some special values that numeric variables can contain that are not numbers. It's worth knowing they exist because occasionally they will crop up and mess with you. All right, let's get back on track. So I was showing you that I could generate repeats of the not applicable value 10 times. There's Batman. Okay. Now, let's now look at a more advanced function. This is the runif command. But more specifically, it would make sense if I were to read this as runif. Does anyone remember the uniform distribution? Uniform distribution. Yes? Ah, cool. Okay. So a uniform distribution is a variable that isn't curved, that isn't bell-shaped curve or anything. It is evenly spread across the space. Now, runif is going to give us random samples from this uniform distribution. Does anyone detect a pattern here, like a minimum or a maximum value?
Yeah, 0.1 decreasing. No.
They are what?
Decreasing by 0.1. No. 0.
No, because the runif function is giving us random draws from a uniform distribution. Okay, so what's the highest value here, or the lowest value here?
0.
There's a 0.9 in here? Okay, 0.997? That's pretty high. But it's not above 1, is it? Okay.
0.20, maybe 0.007.
Oh, you're right there. It's 0.007. James wants us to discuss this today. That's good. So, so what we have is a range between 0 and 1, and it's uniform within that space. It's a little out of series here, but I'm going to just do a quick histogram of randoms. Does everyone remember what a histogram is?
Yeah, barcode.
Yeah, I want to see how common each of these values are. So I'm going to just run hist on randoms, and man, everything blows up. I was looking at text, and now I've got a friggin' figure on the screen. Okay, so the hist function generates frequencies for certain bins of values, and then it produces a plot. All right, and in this case, we generated 100 random values. None of them were below 0. None of them were above 1. And, well, it's kind of lumpy looking, isn't it? But these are still random samples off the uniform distribution. Remember that we had a certain number of randoms. Does anyone remember how many? 100. When you draw 100 values from a distribution, does the distribution look just like the distribution of that it was drawn from? Not necessarily. Okay, so if we were to rerun this, and you can just close that window to get back to your back to the text interface. If you were to rerun this and this time say, I want 10,000 values, it's still going to work. That's weird. Oh, I think I did something wrong here. No, I'm sorry. I botched that. Yes, you can know the language pretty well and still make mistakes. I needed to tell it I wanted 10,000 values here and then perform a histogram on the randoms. I put it in the histograms call instead. I shouldn't have done that. There. Isn't that nice? So now we've taken 10,000 values from it and generated the histogram. Now it looks pretty steady across the 0 to 1 series. What if I don't know the runif command very well? Because obviously I forget things. Let's try getting help on the runif function. So I'm going to say $runif. Suddenly my web browser opens. Okay. So R has a help function that's always there for you. If you have a function that you don't remember exactly how to call it, put in a question mark, type the name of the function, and this will pop up. Is this going to be very friendly advice and help you in the way that ChatGPT will? No, it is not. On the other hand, is it not going to destroy the environment and give you false information? I'm not a fan of ChatGPT. I'm not a fan of any of the LLMs, I have to say. But you can get the manual page, at least, for what that function is supposed to do. And here you can see that our unit form it has 4 related functions. The D function, the P function, the Q function, and the R. Yes. Oh, that is true. It's just web browser text, so I can make that huge. Yeah, I couldn't read that. I would. Okay, so in this case, it's one page describing all 4 of these related functions. And they do very different things, none of which I'm going to go into right now. But I just wanted you to know that you can get help by hitting question mark and a function name, and up it will pop. Okay, I will close that down. Okay, we're back in here. Let us return to the scripted stuff. In this case, I would like to perform 3 different summaries of my random variables. I'm going to close the histogram because it's not part of the script. Right. One of these functions is my very favorite in all of R, and I probably use it every 3 or 4 lines because I can never remember stuff. So we start with mean randoms. We don't like these randoms. Why? Because they're mean. This is, however, giving us the arithmetic mean. We have a whole bunch of numbers ranging from 0 to 1. We are computing the mean of them, therefore the mean is really close to 0.5. Okay, so not surprising behavior here. Mean is pretty obvious. Summary, however, is a more detailed description. Now we see the minimum, the first quartile, the median, the mean, the third quartile, and the max. Who quickly remembers what a first or third quartile are? The what? 0.25 of what?
The series, the values of the series that are occurring in the 25% of the data. And the median, which is the value that will split the data.
I got this one. This is good. All right. I have all my numbers. I can sort them from bottom to top. And then I can say what's in the middle of that list. That is our median. Then I can look at the list to its left and say what's the middle of that. And that's the 25th percentile. Or I can ask what's in the middle of the list on the other side of the median. That's the 75th percentile. Okay, so if you want to know the distribution of a long vector, summary is a very good friend because it gives you all of that right away. And finally, we have the length of the randoms. Here, we're using this call right up here where I specified it should be 10,000 values, so we have 10,000 randoms. As written in the script, I think it was 100. I would also say if you're really keen on seeing all of the variables, you could do something like this. Plot sort randoms. So if we do this, once again, it's going to throw together an image for us. Here we had our 10,000 values sorted from smallest to highest, and you can see that they form a straight line because this is a uniform distribution. Okay. Usually more interesting, but with uniform distributions, you get what you get. Okay, so summary is definitely my favorite. It'll show up a lot as we move along. Now, I'd like to talk about factors because factors are very, very special sauce in this software. All right, so I start with fruit. Fruit is equal to just those values that we threw in there. Oh, is something going on? Did it kill your laptop? Oh, it's good. Okay. I thought I would check. Sometimes noises mean something's gone really badly, and I'd like to help you solve it. Okay, cool. All right. So fruit is comprised of it comprises a vector that's been created by the compose function from apple, pear, banana. But fruit f is a different variable. It's been created using the factor function. Now, fruit is still that happy little vector that shows up there, but fruit f is different. Why is that different? Very nice. Spotted it right away. Okay, so I repeated apple and I repeated banana. So there are 3 distinct values, and the software is able to recall that there are these 3 levels, and this is the sequence that they came in. These are no longer strings, though. These are now levels of a factor, and it's a little different. So as examples of that come along, it's really valuable. So if you have 10,000 values in a spreadsheet, and you want to know how many distinct values are in this spreadsheet, this software is for you. Factors can pull out that information really quickly. And here's how you do it. So you can use the levels function on the fruit factor, and out will pop the 3 distinct values that appear. All right. Now, let us look at vectors that might show up in an actual study, say. I'm going to start by just putting in these first 2. So I have a vector comprising character strings, M, F, M, M, F, and M. Then I make a factor from that called sex F. And now I would like to know how those distribute graphically. And right away, I'm able to see I had more M's than I had F's in this particular study. Not quite a manual, but it's getting there. So we would like to know all distinct values that appear here. Now, my wife works in history, and she ran into a really interesting problem with one of the data sets they were given for class, that it was a spreadsheet that had been added to by many different people over many different years, and they had different ideas about how to code stuff. So sometimes it said male, sometimes it said female, sometimes it said M, sometimes it said F, sometimes they had that little symbol, the symbol with the arrow pointing up or the plus hanging down. Yeah. So when you see stuff like that, it can really, really cause you grief in your statistics. And doing simple things like making a factor off of them and asking how many distinct levels there are can save you a lot of hassle. So if you suddenly discover there's a 3rd sex or 5th sex in a table, and you weren't expecting that, then you can detect it quickly. Okay. Grand. Let us return to this. It's time to talk about matrices. Does everybody love matrices? Is that just me? It's just me? I'm so sad. All right, let's talk about matrices because they're valuable. They can save us a lot of hassle sometimes. In this case, I have 6 values that I want to pass to create, but I don't want them to be stored as one long vector of 6 values. Instead, I want to specify that there are 2 rows represented by these data that I'm passing it, and I want it to create a matrix with rows and columns as a result. All right, there's this little, okay, so we have different things going on. We've got a function here that's combining these 6 values into a vector. We have parameters. I don't think you've seen named parameters yet in a function. We're passing it the value true for by row, and we're passing it the value 2 for the variable n row. And all of that is getting passed into the matrix function that is then generating this. Okay. Are we okay with this so far? Now, you'll note that there's this business with brackets over the columns and brackets down the rows. And it's trying to be helpful here, but I think it's maybe not the most clear of naming. What the software is trying to tell you is that there is a row 1 and there's a row 2, and there's a column 1 and a column 2 and a column 3. What's the business with commas? The business with commas is that R is trying to remind you that rows are given first when you're trying to pull a value out of a matrix. So if you ask this matrix for just the 1 comma set, you're going to get the first row. If you ask it for the 2 comma set, you're going to get the second row. If you ask it for the comma 1 set, what results? The first column. You get the values 1 and 4. Okay, so when you've got data in a table like this, in a matrix like this, you can do all kinds of very, very spiffy math operations quickly. All right, I want to follow. All right, we're going to add some names to make this prettier. Is that okay? Because I mean, it's often helpful to me to do this with a complex matrix. In this case, we are providing new names to the matrix called mat through the dim names function. And what is being fed are two different vectors. There's the row 1 and row 2 vector. There's the call 1, call 2, call 3 vector. These are being put together in a list with these two vectors side by side, all of that being jammed into the names of mat. So let's see what results from that, and then we'll try to talk through it. All right. So I've done something rude to you in that back to back, I introduced matrices to you, and now I've suddenly introduced a new thing called a list. So let's look at just the right side of this naming thing we did. Who, by the way, is my lunchtime checker? Yeah,
You still have 20
minutes. 20 minutes. 20 minutes? 20 minutes, okay. This is an important duty. I mean, he's on the task. This is good. All right. I said I just introduced to you both lists and matrices. So what is a list? A list is a heterogeneous list of stuff. In this case, we have a vector, row 1, row 2, and a vector, call 1, call 2, call 3, and we put them in a list of which the first element is row 1, row 2, and the second one is call 1, call 2, call 3. Okay, so there's no real requirement that a list have items of the same type or of the same length or of the same name. They can just be whatever you want. It can be, here's the Dave Tab favorites list. Star Wars A New Hope, 73, green, 5'9". We don't know what 5'9" means here. That's okay. It's definitely not 2 meters. So what you had there was sort of like a favorites of Dave, but they were unspecified in type or in order. In this case, the list is going to remember things in the order you give it to them. All right? In this case, dim names needed to receive that list in order to know what the rows were to be called and what the columns were to be called. So having done that, mat looks pretty. Now it has call 1, call 2, call 3 instead of that comma business. Right. We can try a few interesting things here. Let's try a transpose. Does everyone remember from math class what a transpose is? All right, let's look at TMAT to see how it did it. Before, mat had call 1, call 2, call 3 across the 3 columns. Now we see a transposition has taken place. It's been flipped along its axis. That which was a row is now a column. That which was a column is now a row. And so this has resulted in doing a transpose. Sometimes you need to do that. How frequently have you had an Excel spreadsheet and realized that the things that you had on columns really needed to be on rows? Mm-hmm. Is there a handy-dandy retranspose function?
Yeah, you paste as
paste special. Very nice. Very nice. You guys have been in the trenches. I can tell this. Yeah.
And if you multiply them, you get the identity matrix.
Very nice. The identity matrix does indeed fall out. Yes. I wasn't going to go into that. Frankly, I don't remember that much of matrix math. Did you take? Yeah, I bet you took like linear algebra and stuff like that. That'd be very useful for an awful lot of biology. Things you miss in undergrad that you don't realize. You know, I was implored to take an immunology class when I was in grad school because my PI really wanted me working in that. I was like, I find that field completely incomprehensible. I don't know where to start with immunology, so I didn't take it. And then I ended up doing work with antibodies and stuff. I'm like, dude, I wish I took that class. He was right, totally right. All right, transpositions, you can do them very quickly here. Sometimes we're going to add new stuff to these data combinations. So let's add a third row to Matt. Remember, Matt is looking like this. And now we've just created a new variable that has 7, 8, 9. We just want to stick it on the bottom, right? So here, we're going to create bigger Matt that uses the row bind function. rbind is row bind. And as a result, bigger Matt now has a new row added to it. Okay? So you can do a lot of magic really quickly. Can you also mess things up really quickly? You bet. You bet. I'm very good at that. I can tell you 1,000 ways to do that. Okay. So I want to talk a little bit about distributions. So let us build samples from a uniform distribution, a normal distribution, and a Poisson distribution. Okay, so that's all very quick. We're only grabbing 100 values from these distributions, and very swiftly, we can plot them. Okay, I'm going to tile these vertically so we can see both the text. All right, so that's the histogram of our uniform distribution. That all looks pretty ordinary. Those are uniformly distributed between 0 and 1. Let's look at our normal distribution. Yep. Here's our normal distribution. Does that look normal?
Your data, need more data.
You got it spot on, exactly. Yes, if you try to make a normal distribution look right with just 100 samples, you're going to have a lot of sampling variability. In fact, your plot probably looks quite different than mine because yours generated a different set of random numbers than mine did. Okay, good call. All right, and finally, the Poisson distribution. Anyone remember what the Poisson distribution is good for? I have kind of a weird example that comes to mind when I think about the Poisson distribution. These days, most everyone's using like LED and compact fluorescent lights. But in the old days, we had incandescent lights. And incandescent lights occasionally would surprise you when you entered a room. You'd enter the room, flip on the light switch, there'd be this bright flash and maybe a faint smell of ozone, and you'd know your light bulb just blew out. So I find myself thinking about the Poisson distribution as a way to estimate the variability as you flip on the light switch going into a room 10,000 times. But it's probably a pretty poor example of it. But if you have count data and you want to understand their variability, the Poisson distribution is a pretty good way to deal with that, to model the variability in collections of data. Okay, so there's Poisson. All of these are just distributions built into the software, like the gamma distribution, for example, because the software expects that you might well need them, and these few canonical distributions show up all the time. And if a distribution you want isn't supported by base R, there is certainly a plugin that will support, say, the Gumbel distribution or whatever. So you have lots of options available to you outside what ships with R. We will be talking extensively about the use of ggplot2, which is a really big library of software for R. Okay, right. We're going to run a t-test. It's a stats class. We have to talk about a t-test. It's part of the statutory requirement, isn't it? All right, so let us do a t-test. I have A values, I have B values, and then I performed a t-test on them. Let's walk through it. Here, I'm not using R unif anymore. I'm using R norm, okay? And that's because I wanted to have a normal distribution, a bell-shaped curve that I'm pulling values from. I'm going to grab 10 values from the normal distribution. This one has a mean of 3. The other one, I'm also going to grab 10 values for B, but these come from a different distribution, and it's different because the mean is not 3, it's 5. Okay, so I'm going to have 10 values dancing around this, and 10 values dancing around that. In C, I perform the t-test under default situations with A and B, and ask, are they different? So here are my values for A, here are my values for B. We could do some quick eyeball tests to say, what's the range of these variables, what's the mean of them, and so on, from the ones that I've actually sampled here. But all of that will be handled by the Welch test anyway, so that's okay. So I now perform a t-test using the t.t-test function, passing it A, passing it B, and out pops a list with some nice formatting attached to it. but a list nonetheless. So things like the p-value show up in text here, but there is in fact a variable behind the scenes that you can pull out. I think it's called p.value. It's not really a big mystery. So in this case, the p-value is definitely below 0.01, nice and low. Degrees of freedom is about 18. We had a t-statistic of minus 4.7. We get a confidence interval out. We see that the means were in fact different. Did the means look like the variables that went into it? The mean of A was supposed to be 3, but here was 3.02. That's a pretty well estimated mean, I'd say. The other was 5.66. It was supposed to be 5. So the B variable on mine was a little bit higher in mean value than I expected it to be, because it was just a few values sampled from the normal distribution. Okay, so all of that's just built in. This is not the only way that we could run this t-test. If I wanted to have some options that I could use to customize how the t-test was performed, say to make it cited or to make it a one-sided test rather than two-sided, how would I do that? Does anyone remember getting help on a function? Question mark. Righto. So very quickly, I could just do a quick question.t.test. Up pops the help. And if I have it blown up in a few font sizes, I could probably read it myself. Yeah. Great. Okay. Now, C has kind of a complex structure to it. So let's look at two ways we can evaluate its structure. Let's try type of. We see that the t-test value is returning a list, but when I just told it to show me the value of C, I got back what looked like nice text. So let's also examine the structure of C. Well, now we see that it's actually a list with 10 different elements, including statistic, parameter, p.value, confidence interval, etc. All of that is there. And in fact, we can pull out particular items of it. I said that there was a p.value in there. Here it is. It's yet another symbol for us to remember. Here's the dollar sign. Okay, so in this case, we have a list with named elements, named fields. And p.value is one that we want to extract out of what was returned by t-test. So I saw a p-value where? It's right here. P.value, it's a numeric, its value is 0.000149. Here I've now yanked out that value independently of the list so I can save it somewhere else or, put it in a poster for all that. Okay. So we talked about using the square brackets to lift out things like a row from a matrix or a column from a matrix or an individual cell from a vector. We've also now talked about the dollar sign operator for pulling out a named element of something. If you have a data frame, which is going to be a big deal, that's going to show up soon, or I have a list coming back from a function and I want to extract particular named values out, the dollar sign operator is very helpful for that. Okay, this already feels like way too much for a first lesson. How's our lunchtime planning? 2 minutes. No. Oh, we have 10 minutes. All right. I thought I'm stopping here. Whoa. Okay. Let's talk then about data frames. Now I'm going to run this top section and we'll just walk through this. I have in this case label, reading, and a data frame. I'm not going to play that. Okay. So again, we have a complex compound function. I have 5 repeats of the word case, followed by 5 repeats of the word control, and that's all jammed into the value label. I have 10 readings. Those have all been jammed into a value called reading. Then I use what's called a constructor. I am making a data frame that contains labels and reading, and shoving that in something called df. Now, when I play back df, something magical happens. It's all combined together. My columns have names that reflect where they came from. One was a variable called label, one was a variable called reading. It's got 10 values in it, and they're lined up. Now, is this a matrix? It's not a matrix. It's not a matrix because they don't all have the same type. Because those things on the left are not yet a factor. Those are strings still, or character strings. The things on the right are numeric values. So can we prove that to ourselves? Let's run a summary. I see that there are 10 labels. There are 2 unique values of it. None of them were blank. The minimum number of characters was 4 and the maximum was 7. Or 7. Pretty straightforward there. Reading is interpreted as a bunch of numbers. Okay. So label in this case was not interpreted as a factor because it doesn't detect that there are just 2 different levels and it stores each as an instance of that. But it's pretty close already. Okay. I want to point out that you can write your very own functions in R. And you don't have to write them in C or Fortran or whatever crazy thing you want to. You can just write them in R. Does everyone remember the Pythagorean theorem? I taught this course in China once, and they're like, we don't call it the Pythagorean theorem. I'm like, you wouldn't, would you? They call it the rule of right triangles. That's a very sensible name for it. Anyway, Pythagorean theorem is useful when you're trying to find a distance between 2. Here we've created a function using the function. Yes, you knew we were getting there. R is just like this sometimes. The function creates functions. It is what it is. All right. In this case, the Pythagoras function is going to work with variables x1, y1, x2, y2. But you see this equals 0 business? Sometimes the users won't provide all 4 values. And if they don't, these 2 are going to get set to 0. Then it's going to compute the absolute distance on the x-axis, the absolute distance on the y-axis, square them. See this little hat 2? I haven't shown you that before. Hat 2 means square, right? So y-diff times y-diff, x-diff times x-diff. We're going to add those 2 together, compute the square root. That's the distance. And distance gets returned to the user. Okay. Creating your own functions. Does it make sense that this is creating a function? Does having default values for variables make sense? Let's see how this plays out, though. Let's actually use our new function. All right, I called it Pythagoras, so let's do it. Where was Pythagoras working? Ithaca? All right, that's fine.
Aegean.
In the Aegean Sea. Ah. Well, that's disappointing. I mean, it could have been on Crete, right? All right, that's fine. What?
Yes. Guy who was traveling for 20 years to go back with his wife.
Pythagoras was with...
No.
What? Oh. With the Odyssey.
Yes.
Yes.
I
All right, which island do I need to be thinking of for Pythagoras? Samos. All right, another place I got to visit. All right, so I've used Pythagoras, new function. The function created a new function called Pythagoras. We're calling the Pythagoras function, giving it 3, 4. How is the software working? It needs 4 values, right? Remember, we said x2 and y2, if no one provided them, would be 0 and 0. So Pythagoras, receiving the values 3 and 4, says x1 equals 3, y1 equals 4. I'm going to run all these operations on it, and what it returns is 5. Is that a correct answer? Yeah, because a right triangle with sides 3 and 4 has a diagonal of 5. Great. Wonderful. Let's see if we can find the distance between 2 points. Also works. In this case, x1 takes on the value 1, y1 takes on the value 6, x2 takes on the value 4, y2 takes on the value 10. And the answer is still 5, because 1 and 6 are 5 apart, 4 and 10 are 6. Sorry, 1 and 6 are 5 apart, 4 and 10 are 6 apart. Yeah, right. So that's kind of handy. You can create your own functions when R doesn't include something that you want it to do. It is 27 minutes past the hour, and that means we are not going to lurch into the next part of the demo today. There's a whole lot we didn't cover, right? We didn't cover things like for loops, conditional operations. So there's stuff that we should talk about. We'll try to cover that as we move along. But as we do the next 3 sessions, there's going to be a pretty strong graphical emphasis on what we're doing. And we'll be moving much more heavily into gene expression as our examples, rather than just simple examples that we put together. Okay. Are there any questions before we shut down this and go ravage whatever food is outside? Oh, it looked like you had a question ready to go. No? All right. Yes, sir.
DF2 or only mammals?
Okay, so that's an interesting question. So a data frame like this is not a matrix. So can I run the transpose function on that? That's pretty wild, but it does in fact work. Yeah. I didn't think it would, but it did. I've never tried taking the transpose of a data frame. Now I have. Thank you. Okay. Any other remaining questions? Is everybody excited about coming back at 9:30 tomorrow morning?
Yes.
Actually, yeah.
Great. Great. Okay, let's go demolish some lunch.
Thank you very much.
Oh, you're welcome.